Harshigowda, Harshigowda, Janvi,
Present, sir.
right? Mahadev,
Present, sir.
okay. Mahadev, Mahadev, Mohammad,
Present,
Mohammad,
sir.
right? Kirti, Kirti, Pikesh, Pikesh, Prajwal Gowda,
Present, sir.
right?
Present, sir.
Ramesh,
Present, sir.
okay. Ratan,
Present, sir.
right? Rohan, Rutik,
Present, sir.
okay. Rutvik Gune, Rutvik Gune, Sadashiv, Sadashiv, Sagar, Sai Prakash,
Present, sir.
right? Samir Ahmad,
Present, sir.
okay. Sania,
Present, sir.
right? Sanjay, Sankalp,
Present, sir.
okay. Sanket, Sanket, Shiraj, Shiraj, Shivnanda Natikar, Shivnanda Natikar, Shraddha, Shraddha, Shubham, Shubham, Sumit,
Present, sir. Present, sir. Shubham.
okay. Sumit, Sumit, Suraya Banu,
Present, sir.
okay. Tejas, Tejas, Vivek, Vivek, Yamnappa, Yamnappa, गावकर रजत रामचंद्र, गावकर रजत रामचंद्र, मंजुनाथ, मंजुनाथ, प्रथमेश,
Present, sir.
ओके. जोसलिनो, Joslino, right. In the last class, we stopped at the approximate hybrid model. Approximate hybrid model, that was the topic of the last class. Are you able to see the screen here? Screen is visible? Screen is able to see? Are you able to see the screen, students? Students?
Sir.
Screen is able to see, no?
Yes, sir.
Fine. So in the last class, I gave just refreshed about the hybrid model of common base configuration. This is how it looks. Common base configuration. These are the fundamental equations. Right. Then coming to hybrid model of common emitter configuration, fundamental equations, and how they are converted into VBE, that is HIE-IB plus HRE-VCE, and IC is equal to HFE-IB plus HOE-VCE. This is for the common emitter configuration. Then this is the model of the common emitter configuration, hybrid model, right? Then coming to the common collector configuration, hybrid model, these are the fundamental equations and they get converted into this form, right? Where the input voltage is VBC and the output current is IE for the common collector configuration. This is the hybrid model of the common collector configuration, where we have the collector common between the input sections and the output section. Input current is IB, input voltage VBC, output current IE, and output voltage VEC. Then later I explained the approximate hybrid equivalent circuit. This is how it looks like. Consider the hybrid equivalent circuit of the below figure. Consider the hybrid equivalent circuit of the below figure. Right? This is how it looks. The input voltage is VI, input current is II, right? then output current is I0, output voltage is V0. And we have the HI resistance, HR V0 controlled voltage source, HFII, the controlled current source, and the output resistance H0. Okay, this we discussed in the last class, right? This is our, that is a total hybrid equivalent circuit. This gets converted into approximate hybrid equivalent circuit. That is the values of HR and H0 when they are not included, right, in the model, then the performance parameters Zi, Z0, AV and AI are slightly affected. When HR and H0 are not included in the model, the performance parameters AV, AI, HR and Zi and Z0 are slightly affected. Hence, these values are considered as approximately equal to 0. HR B and HRE are approximately considered equal to 0. So when HR becomes equal to 0 approximately, then HR V0 also becomes 0. That means this HR V0 is considered as a short circuit. This HR V0 is considered as a short circuit. That is, we had discussed in the last class. Due to small values of HRE and HRB, we can take their values as approximately equal to 0. That is, HR V0 will be equal to 0. When HR V0 becomes equal to 0, that means this becomes a short circuit. This is a voltage source and hence it becomes a short circuit. Therefore, it is represented as a short circuit here. The controlled voltage source is represented as a short circuit, and the output resistance, this HO, the output resistance or the admittance 1 upon H0, it is very large as compared to the load resistance that is connected between the output terminals. The output resistance H0 is very large as compared to the load resistance RL connected between the output terminals. We know that when the resistance is very large, the current is almost to 0. It is negligible. Hence, this H0 is considered as a open circuit. Because of the large value of resistance, the current flowing through the resistance is very less. It is almost 0, negligible, and hence it can be considered as a open circuit. Remember, this is only for the circuits which are having large values of H0. Which are having large values of H0 or 1 upon H0. Only for such circuits, this holds good. Otherwise, we have to consider H0 in the model. Clear yet? Therefore, here the HR V0 will become equal to 0 and the output H0 will be open circuited. The output H0 will be open circuited. Therefore, the approximate hybrid equivalent circuit looks like this. This is the approximate hybrid equivalent circuit where the in controlled voltage source HR V0 is a short circuit and the output resistance H0 is a open circuit. Further, we have HI only in the input side here. Therefore, this circuit gets modified into, and in the output side we have only HFII. Therefore, I can redraw this figure. Like this. So where we have the input voltage VI, input current II, then HI is the input resistance, then controlled current source is HFII, output current is I0 and output voltage is V0. So this we have got from the approximation that what we have approximated, the controlled voltage source is 0 and the output resistance is open circuit. So based on this assumption, we are getting the total equivalent circuit, hybrid equivalent circuit getting converted into approximate hybrid equivalent circuit. This is our approximate hybrid equivalent circuit. Right? Then we have the approximate hybrid equivalent circuit for the common emitter configuration and the common base configuration. This is the generalized circuit. This is generalized for all, that is common emitter, common base and common collector. But when we want particularly for the common emitter configuration or for the common base configuration, then this current HI will be the input current. This HI will become HIB or HIE for the common emitter. This is for common emitter configuration. Input current is the base because emitter is common between the input section and output section, right? Therefore, we have the input applied to the base terminal. Okay, input is applied to the base terminal, that is IB. Fine, and then the output is applied at the output is coming from the collector terminal. As we know, according to the convention, they have to take an inside. Therefore, IB and IC are shown flowing inside the two-port system, inside the circuit. Then we have the HIE here. HIE, as it is common emitter, therefore this HI should be taken as HIE, and as it is common emitter, this HF becomes HFE and input current II is base current, therefore this becomes HFE IB, HFE IB. and the output voltage is VCE between collector to emitter. Therefore, this is the hybrid equivalent circuit, approximate hybrid equivalent circuit for the common emitter configuration. Are you following here, students? Yes. Are you following here? Students, are you following here? Sumit, are you following here? Sumit? Shubham? Shubham? Are you following here? Shubham? Suraya Banu? Suraya Banu? Suraya Banu? Ankita, are you following here? Ankita? Ankita?
Yes, sir.
Clear up till here? Any doubts up till here?
No doubts, sir. Understood.
Okay, right. Next, we'll see the approximate hybrid equivalent circuit for common base configuration. This is for common emitter. The main circuit, this is our approximate hybrid equivalent circuit, a general one. This gets slightly modified for the common emitter, common base, and for the common collector. Now, this is for the common emitter configuration. Similarly, we can have for the common base configuration. This is for the common base configuration. Just note here, this is HI will become HIB. This HI is there. This will become HIB. Then HF, this will become HFB, and input current for the common base configuration. For the common base, it is IE. Therefore, this becomes HFB IE. That is, input current is IE. In resistance is HIB. Then we have input voltage VEB. The controlled current source HFB IE. Output current IC and output voltage VCB. That is, base terminal is common between the input sections and the output sections. That is, it is the common emitter, common base configuration, hybrid equivalent circuit, approximate one. Okay. Then we'll see the relation between the parameters of hybrid model and the RE model. Relation between the parameters of hybrid model and the RE model. This is what you are seeing on the left side. It is which model? Can you tell me? Left side is which model? This one. It is which model? Chandrasekhar. It is which model? Janvi. Janvi. This left side is which model? Either it is hybrid model or RE model. Mahadev. Mohammed. Prajwal Gowda.
Sir, it's hybrid model.
It's a hybrid model, correct. Left one is the hybrid model and the right side one is the RE model. Just by looking into those parameters only, we'll come to know. H is there. See here, H is there. Here also HFE is there, right? So if we look into those, then we'll come to know that they are the, or it is a hybrid model. Here there is a RE, AC resistance, RE. Therefore, the right side one is the RE model. This is for the common emitter configuration. Common emitter configuration. This is the hybrid model. This we have already studied, and the RE model for the common base configuration, common emitter configuration also we have already gone through. We have already studied this. I'm just putting one by the side of another. This is the hybrid model for the common emitter configuration, and this is the RE model for the same common emitter configuration. So if we put both of these side by side, then what is the relation between the hybrid model of common emitter configuration and the RE model of the common emitter configuration? That we have to compare. So that we have to see. Here if we see, this is HIE, this resistance, right? Both are almost similar. Therefore, this HIE is nothing but beta RE. If you look into both, the main structure of the both is same. Here it is HIE, here it is beta RE. That means HIE will be equal to beta into RE. Then here it is HFE IB, here it is beta IB. That means HFE will become equal to beta. HFE will become equal to beta. This is the relation between the parameters of hybrid model and the RE model for the common emitter configuration. What is the relation? Here there is resistance HIE, here it is beta RE, both are same in structure. Therefore, HIE is equal to beta RE. Then here we have the controlled current source HFE IB. Here it is beta IB. IB is same. Therefore, HFE will become equal to beta. HFE will become equal to beta. Right. Then the same is highlighted here. Comparing the two models, we obtain the relations. That is, HI will be equal to beta RE and HFE will be equal to beta. HIE is equal to beta RE and HFE will be equal to beta. This is the relation between the parameters of hybrid model of common emitter configuration and the parameters of the RE model of the common emitter configuration. Next figure shows the approximate hybrid model and RE model comparison for the common base configuration. Just now we saw it is for the common emitter. Next one is the relation between parameters of hybrid model of the common base configuration and the parameters of the RE model of the common base configuration. If we look into both of these, again we have already studied all these models, that is hybrid model of common base configuration and the RE model of common base configuration. I am just putting the figures side by side, right? If we observe the two figures, here it is HIB resistance, here it is RE resistance. That means HIB is equal to this resistance RE. HIB is equal to this resistance RE here, right? And if we see this controlled current source, this is HFB IE, this is alpha IE, HFB IE and alpha IE. That means HFB will be equal to alpha, HFB will be equal to alpha. That is the relation is HIB is equal to RE and HFB will be equal to alpha, because both are similar in structure. It is the same configuration, common base configuration only, just the models are different, but the same structure is there for both the hybrid model and the RE model. Therefore, the parameters relation will be like this. That is, HIB will be equal to RE and HFB will be equal to alpha. Here there is a point regarding this configuration, this common, that is base configuration. If we look into this figure, the value of alpha, we already defined this formula alpha for the common base configuration. Alpha is given by output current by input current. As there is a beta in common emitter configuration, beta is given by IC upon IB. Similarly, in common base configuration, alpha is given by the output current IC divided by input current IE. Alpha is equal to IC by IE. But if we look into this, then the value of alpha, right, the emitter current and the collector current are flowing in the opposite directions, right? If we are considering either NPNP or NPN, the I and IC are in opposite directions. Therefore, the HFB or that is HFB is nothing but here it is alpha, because HFB is equal to alpha. What is the relation we have got? HFB is equal to alpha. This alpha is equal to IC by IE. This should be taken as negative, because the two currents, emitter and the collector currents, are in opposite directions, right? If we see the directions of the emitter current and the collector current, right, by normal convention itself, the directions are opposite here for the emitter and the collector current. Therefore, we have to consider the value of alpha as negative. Alpha is equal to minus IC by IE. Alpha is equal to minus IC by IE. That is how we are getting this. HFB is equal to minus alpha. There is a negative sign will come in the formula of alpha, that is minus IC by IE, or HFB is equal to minus alpha. And we know that alpha value is approximately equal to 1. Alpha value is approximately equal to 1. Therefore, HFB will be equal to approximately minus 1. We can write HFB is equal to minus alpha, that is equal to minus 1. Like this, we have got the value of HFB or the alpha value for the, that is for the RE model, or for the relation between the parameters of hybrid model and the RE model. Next is approximate hybrid equivalent circuit of the fixed bias configuration. Approximate hybrid equivalent circuit of the fixed bias configuration. This we know, we have studied this in module 1 itself, the fixed bias configuration, where we have the base resistance and the collector resistance. Here, what about the common collector configuration? Can you tell me which is the common collector configuration? Which is the common collector configuration? Have you studied the common collector configuration? If yes, and which circuit is the common collector configuration? Just now we dealt with common emitter and common base. Correct? Common emitter and common base. What about the common collector? Common collector circuit, have we studied? Have we studied that? Can anybody recollect which circuit is that? Common collector configuration. When I was discussing that circuit, I mentioned there that this circuit is also called as common collector configuration. Which is that circuit? Which is that circuit? Can anybody recollect? Ramesh? Ramesh, can you recollect that? Ratan? Ratan? Yes. Ratan?
Left hand side, sir.
Which one?
Left side.
No, not. I'm not asking that. I'm asking common collector configuration. There is a particular circuit that we have studied, and which is called as common collector configuration. Which circuit is that? I'm not mentioning that this or this. I'm not asking in this figure. What I am asking is the common collector configuration we have studied. Have you studied or not common collector configuration?
Emitter followers.
Very good. Excellent. Common collector configuration is emitter follower, right? Emitter follower circuit we have studied, where the emitter follows the output at the emitter follows the input at the base terminal. Correct. In the emitter follower circuit, we have the resistance connected only between one resistance is connected at RB, that is to the base terminal. Another resistance is at the RE, emitter resistance, capital RE. Right. There is no collector resistance in the emitter follower circuit, is it not? So that is nothing but emitter follower circuit is nothing but the common collector configuration. Remember, in examination they may ask it as common collector configuration or the emitter follower. Both mean one and the same. Okay. So in that emitter follower circuit or the common collector configuration, there is a resistance RE will come here. So one more resistance RE will come here. If we are explaining the relation between parameters of hybrid model and the RE model, right? This RE resistance will come here between this junction of RE and alpha E, and to the base there is a resistance RE, capital RE. If you can recollect, right? There is a capital resistance RE, capital resistance RE connected between the junction of RE, small RE and alpha IE to the base. Therefore, we have to consider that RE also, and that is slightly complex, right? That is not mentioned. Therefore, we are not considering that. That is the RE model relation between parameters of hybrid model and the RE model for the common collector configuration, because that RE resistance will come here in between the junction, but for the common emitter and the common base there is no resistance as such. Only this small RE is there, only this small RE is there, and the alpha I. But if we are defining that common collector configuration, that is capital RE will also come at the emitter terminal, because the output we are taking at the emitter terminal there for the emitter follower, and the input is applied to the base, right? So that is a different thing that we are not considering here. We are just concentrating on the common emitter and the common base configurations. This is the fixed bias configuration. This we have dealt in module 1. We have resistance RB connected RC. There is no emitter resistance in fixed bias configuration. As there is no resistance here in the fixed bias configuration, the emitter resistance is not there. Then this is our approximate hybrid equivalent circuit of fixed bias configuration. We have resistance RB. How will we get the AC model or the RE model? AC model we are getting from the grounding the VCC. We are grounding the VCC source, correct? When we ground this VCC source, this resistance RB will come in between base to ground. Resistance RB will come in between base to ground. Therefore, the RB is connected between base to ground or base to emitter here, because emitter is common between the input sections and the output sections. and resistance RC is connected from the collector terminal to ground. This VCC is 0, it is connected to ground. Therefore, RC is connected between the collector terminal to ground. It is RC is connected here between collector terminal to ground. This is our RC, last resistance, RC. Right? It is connected between collector to emitter or collector to ground. Then here, one more resistance, HIE. HIE, this is from where we are getting this HI and HFE IB and 1 upon HOE. This is our approximate hybrid equivalent circuit that we studied just now. Just go back and we'll see there. Approximate hybrid equivalent circuit. This is HF common base. It is for common emitter. Here it is. This is HIE and HFE IB. HIE resistance and HFE IB controlled current source. This is for the common emitter configuration. Yes or no? Common emitter configuration. Therefore, this is replaced there. This we are directly taking from here. Again, we are not analyzing that. Directly we take from the approximate hybrid equivalent circuit of the common emitter configuration. This we are taking. That is HI is there, HFE IB is there, and just we are putting it here. Just we are putting it here. So HI is there and HFE IB is there. Common emitter configuration. Then 1 upon HOE is there here because the resistance, output resistance, this 1 upon HOE is nothing but our output resistance, R0. Right? This R0 or 1 upon HOE is not very much large. Therefore, we have to consider this. That's what I mentioned when I was explaining there, that if the resistance is not large, then we have to consider the output resistance 1 upon HOE or R0. Therefore, we are considering it here, but we are shorting the input voltage source, and from there we are getting this HIE at the input. HIE is there, HFE IB is there, 1 upon HOE or R0 resistance is there, then this RC and RB. This is our approximate hybrid equivalent circuit of the fixed bias configuration. Approximate hybrid equivalent circuit for the fixed bias configuration. Understood here, students, this approximate hybrid equivalent circuit of fixed bias configuration. Any doubts here? Any questions here up till now? Any doubts? Sai Prakash? Any doubt?
No, sir.
Clear up till here?
Yes, sir.
Sania? Sania? Sankalp? Sankalp? Any questions, Sankalp? Followed up till here, Sankalp? Shubham? Shubham? Suraya Banu? Suraya Banu? Pratmesh? Pratmesh? Clear up till here, Pratmesh? Ankita, is it clear?
Yes, sir.
Ankita, understood up till here? Any questions, Ankita, up till here?
No questions, sir. Understood.
Understood, fine. Last part of this, I'll just finish it off. Approximate hybrid equivalent circuit of fixed bias configuration. Here we are defining the performance parameters. ZI, it is input impedance. ZI is nothing but RB parallel HIE. This is the input impedance or the resistance seen from the input terminals, that is between base to emitter. Therefore, the RB resistance will come in parallel with HIE. RB resistance will come in parallel with HIE. Therefore, the input impedance ZI is RB parallel HIE. RB parallel HIE. RB parallel HIE. That is input impedance. Similarly, what is output impedance? Can you just look into the output circuit and tell me what will be the output impedance? Z0. We are looking from the in between collector to emitter terminal. Here, this portion between collector to emitter terminal. From this side, we are looking from the output side. If we look from the between collector to emitter terminal, what will be the output impedance? This is 1 upon HOE, this is RC. What will be the output impedance? Just think, what will be the output impedance? Janvi, can you just think? Janvi,
Yes, sir.
just think, what will be the output impedance? Z0. Here one resistance is 1 upon HOE or R0. Another resistance is RC. What will be the output impedance? How the resistance are connected here? How the resistance are connected? Are they connected in series?
Parallel, sir.
Parallel, very good. If they are connected in parallel, what will be the output impedance? If they are connected in parallel. Yes, please.
RC parallel 1 upon HOE.
Very good. RC parallel 1 upon HOE. That is what it is here. Z0 is equal to RC parallel 1 upon HOE or 1 upon HOE parallel RC. Both are the same. Then gain equation AV is given by minus R0 parallel RC by RE. This is taken from the analysis that we did, right? That is gain equation, AC analysis, whatever we did, from that we have taken this gain equation, right? We are not deriving that once again. Just we have to find out the value of AV and AI in terms of hybrid parameters. AV is given by minus R0 parallel RC divided by RE. I'm taking the equation directly from there. What we have already analyzed this fixed bias circuit. That is AV is given by minus R0 parallel RC divided by RE. R0 is here, small R0, it is output resistance. Output resistance is 1 upon HOE. Output resistance is 1 upon HOE. That means R0 will become minus of 1 upon HOE parallel RC this divided by RE. Minus of 1 upon HOE parallel RC this divided by RE. That is minus of 1 upon HOE parallel RC this divided by RE. How we are getting this small RE, that we have to understand. So this small RE is obtained from the analysis here. Slightly we have to analyze that, how we are getting this. Let us see that part. Let us see that. That is, here we have the equation. What is the parallel combination Zi we have? Zi is equal to RB parallel beta RE. RB parallel with beta RE. RB parallel with beta RE. Beta RE. Okay, RB parallel beta RE. This we know from the RE model. Just now what we looked into, RB parallel beta RE. But RB is very much larger than beta RE. Here we know that capital RB is very much larger than beta RE. Is very much larger than beta RE. Okay, so when this RB is very much larger than beta RE, then the resistance will be Zi will be how much? We know that whenever it is a parallel combination of a large resistance with a small resistance, the parallel combination equivalent resistance will be smaller value. Correct. Therefore, Zi will be equal to that is beta RE. It will be approximately equal to Zi will be approximately equal to beta RE. Approximately equal to beta RE. Beta RE. Okay. Now, when this is equal to beta RE, what will be RE equal to? RE will be equal to or approximately equal to the small RE. Small RE will be equal to Zi divided by beta. Small RE will be equal to Zi divided by beta. This small RE is approximately equal to Zi divided by beta. Zi divided by beta. Then we have beta in the denominator. Okay, this is one part. Then another one that we have to find out is, this is RB, we have taken it as beta RE. If we look into this model, here, this is HIE or beta RE. It is both are one and the same. HIE is nothing but beta RE, right? Input side. If we take the AC resistance, it will be beta RE. That is HIE is nothing but beta RE. Correct? Therefore, I have taken HIE as beta RE and I have found the parallel combination of RB and beta RE. Now, if I take the same thing, that is RB and HIE, then what will be the equivalent resistance? RB parallel HIE, that is here, it is nothing but here RB parallel HIE, that is RB parallel HIE. Let's write it, RB parallel HIE. Okay, again this will be equal to smaller value. RB is very much larger than HIE, as RB is greater than beta RE. Therefore, this will be approximately equal to, that is smaller value. It is nothing but HIE. Okay. Now this is nothing but ZIE. That is nothing but ZI, input impedance. ZI is nothing but HIE also. Okay, is also equal to beta R, and that is also equal to HIE. RE is a ZI by beta. RE is ZI by beta. But what is ZI? ZI is HIE according to the second equation here. ZI is HIE. That means this will be HIE this divided by beta. HIE this divided by beta. HIE divided by beta here. Okay, this is divided by beta. HIE divided by beta. This is divided by beta. Okay, so what is beta? Beta is also called as HFE. Therefore, this is HIE this divided by HFE. Beta is also nothing but HFE. I'll tell that how it is HFE. HIE by HFE. If you look into this model here, it is HFE IB, that is beta IB. It is as good as IC is equal to beta IB. That means beta is nothing but HFE. Am I right? IC is equal to beta IB. It is beta is nothing but HFE here. According to our formula, IC is equal to beta IB. Therefore, beta is nothing but HFE. If we substitute here, what we are getting? That is HIE by HFE. HIE divided by HFE. That is our RE. Right? This RE is HIE by HFE. This I have substituted here. From there I am getting this RE, small r is HIE by HFE. Now if we cross multiply this, then we get minus HFE into 1 upon HOE parallel RC, that divided by HIE. Minus HFE, this denominator will come to a numerator if you are cross multiplying this into 1 upon HOE parallel RC, that divided by HIE. This is the gain equation in terms of hybrid parameters, that is HFE, HOE and HIE. This is our normal formula what we have. AV is minus R0 parallel RC by RE. But if we want in terms of hybrid parameters, then it will be this, that is minus HFE into 1 upon HOE parallel RC, that divided by HIE. Last one, current gain equation, it is minus AV ZI by RC. This again is taken from the fixed bias configuration AC analysis. It is minus AV ZI by RC. AV we already know, it is minus R0 parallel RC by RE. This from the previous one, minus R0 parallel RC by RE. This into ZI. ZI is beta RE. Just now we wrote here. ZI is beta RE. This one. ZI is beta RE, approximately equal to beta RE. Therefore, what will be the equation now? That is minus R0 parallel RC by RE. That is AV. This into ZI is beta RE. This divided by RC. Okay, this divided by RC, this RC, whatever is there in the main equation, that is RC. RE and RE will cancel. Okay, minus R0, minus of minus will be plus R0 parallel RC. If we take parallel combination of output resistance and RC, I'm going back to the model. If we take the parallel combination of this R0, that is 1 upon HOE and RC, as the value of output resistance is larger than RC. R0, small R0 value, that is 1 upon HOE, we know that it is very much larger as compared to RC. So when we compare it with RC, it is larger. Therefore, what we have here, according to that, the equation will be, this equation gets changed to minus R naught parallel RC will be simply equal to smaller value, that is RC. R naught is larger than RC, that is RC into beta divided by RC. RC into beta divided by RC. RC and RC will cancel, therefore only beta will remain. That is AI current gain will be approximately equal to beta, that is nothing but HFE. That is how we have defined the equations in terms of the hybrid parameters, all the performance parameters, that is ZI, Z naught, AV and AI. Was it clear here, students? This approximate hybrid equivalent circuit of fixed bias configuration, was it clear here? Yes. Was it clear here?
Yes, sir. Clear, sir.
Clear? Good. So we'll see, just will recap the whatever we studied in today's class. So we started with the approximate hybrid equivalent circuit, Then for the common emitter configuration, this is a generalized circuit. We defined it for the common emitter configuration and for the common base configuration, approximate hybrid equivalent circuits. Then later we saw the relation between parameters of hybrid model and the RE model. Relation between parameters of hybrid model and the RE model. This is the circuit. Okay. From where we got the equations HI is equal to beta RE and HFE is equal to beta. Then for the common base configuration, the relation between parameters of hybrid model and the RE model, that is HIB is equal to RE and HFB is equal to alpha. HFB is minus alpha and alpha is 1. Therefore, HFB is equal to minus alpha, that is minus 1. Approximate hybrid equivalent circuit of fixed bias configuration, then where we drew the approximate hybrid equivalent circuit of this circuit. And from this circuit, approximate hybrid equivalent circuit of the fixed bias configuration, we derived the various performance parameters, that is ZI, it is RB parallel HIE, Z0 is RC parallel 1 upon HOE, AV is voltage gain, it is minus HFE into 1 upon HOE parallel RC by HIE, and current gain AI is approximately equal to beta, that is approximately HFE. Right? I hope everybody followed here, students. Was it understood today's topics? Was it understood here?
Yes, sir.
Mohammed? Was it understood? Rajat Gowda? Ramesh? Clear, Ramesh? Fine. Ratan? Rutik Chopde? Rutik? Samir Ahmad? Kaji?
Yes, sir.
Is it clear today?
Yes.
Today's topic. Okay, fine. Sania? Sanjay? Sankalp? Shubham?
Yes, sir.
Today's topics are clear, Shubham. Any questions?
No, sir.
Okay. Sumit? Suraya Banu? Any problem in understanding? Suraya Banu? Pratmesh? Okay. In the next class, we'll continue with the approximate hybrid equivalent circuit for the voltage divider bias configuration, and we'll solve example on this particular hybrid equivalent circuit approximate model of the fixed bias configuration. That we'll take up in the next class. Thank you.